Let us use an analogy to understand electric flux better. Consider water flowing through a rectangular open channel at uniform velocity and draining into a measuring jar. A valve, V1, is introduced to regulate the quantity of water flowing into the channel. The discharge, which is the quantity of water flowing per unit time, is given by the product of the velocity and area of cross-section of the opening of the regulating valve. To regulate the discharge, we increase the open area of the regulating valve, V1, assuming that the velocity of flow of water upstream remains constant. Let us install one more valve, V2, downstream to V1. V2 is pivoted to the bottom of the channel. Valve V2 can swing about a horizontal axis, which is perpendicular to the direction of flow of water. This completes the apparatus. Now for the experiment. Keep the area of the opening in both the valves the same. That is, the bottom line of the closing plate in the two valves should be at the same height. Measure discharge Q1 for 5 minutes by collecting the water in the measuring jar. Keep this measuring jar away from the downstream flow. Now, lower the closing plate of V1 without changing the position of the plate in V2. Measure discharge Q2 again for 5 minutes. Q2 will be less than Q1 as the area of opening in V1 has decreased due to the lowering of the plate. Then, swing V2 until the bottom line of the plate just touches the top surface of the water in the downstream. Remove valve V1. Measure discharge Q3 again for 5 minutes. You will find that Q3 is equal to Q2. Why is Q3 equal to Q2 when the area of opening of the two valves is different? This is because the area of opening of V2 is more than that of V1. V1 is kept perpendicular to the direction of flow of water, whereas V2 is kept at an angle to the direction of flow of water. The projected area of opening of V2 taken on a plane, which is perpendicular to the direction of flow of water, is equal to the area of opening of V1 that is kept perpendicular to the direction of flow of water. What are the conclusions that we can draw from this experiment? Q is equal to V into A, where V is the velocity of water flow and A is the area through which water flows. In this equation, A should be perpendicular to the direction of flow of water. In the event A is not perpendicular to the direction of flow of water, we should take the projected area on a plane perpendicular to the direction of flow of water. Then, the equation will be modified to Q is equal to V into A cos theta, where theta is the angle that the outward normal to the plane makes with the direction of flow of water. Here, V and A are vectors, and as Q represents the quantity of water, it is a scalar. Mathematically, we can write the equation as Q is equal to the dot product of V and A. Electric flux, phi, is analogous to Q of water. Like Q, phi is also a scalar quantity. However, unlike in Q, where there is flow of water nothing flows in electric flux. There are only imaginary electric lines of force that cut across the area. Uniform electric field E is analogous to the velocity of water V. Mathematically, we can write the equation as phi is equal to the dot product of E and A. We can now extend this equation to curved surfaces with electric field of different magnitudes and directions at different parts of a given surface. The SI unit for electric flux is Newton meter square per coulomb. This brings you to the end of this introductory module on electric flux. You will learn more about applications of electric flux in coming modules. Consider a uniform electric field of strength E along the x-axis. Consider a rectangular surface of area A placed in the uniform electric field such that its axis makes an angle theta with the direction of the field. In other words, the area vector A, which is conventionally taken along the outward normal to the surface, makes an angle theta with the direction of the electric field. The electric flux passing normal to this area is then given as phi is equal to E dot A or phi is equal to EA cos theta. Now, consider a closed surface S placed in the uniform electric field of strength E. Consider three elements X, Y, and Z on the closed surface having areas delta A1, delta A2, and delta A3 respectively. The electric flux through the element X is phi 1 equal to E dot dA1, and since the angle between the direction of the electric field strength E and dA1 is acute, the flux phi 1 through this surface is positive. For all such elements, the flux passes from the outside to inside. That is, they have an inwardly normal flux. Since theta is equal to 90 degrees for element Y, the electric flux for Y is equal to 0. For all such elements, the flux through the surface is 0. Similarly, since theta is obtuse for element Z, the flux through the element is negative. For all such elements, the flux through the surface passes from the inside to outside. That is, they have an outwardly normal flux. From these observations, we can say that the inwardly normal flux is negative and the outwardly normal flux is positive. Let us now consider a point charge plus Q placed at the center of a sphere of radius r. Let us now look at Gauss' law, which defines the relation between the net electric flux through a closed surface and the charge enclosed by that closed surface. This law is of fundamental importance in the calculation of electric field strengths. The closed surface is referred to as the Gaussian surface. The electric field lines of the point charge plus Q are outwardly normal to the charge and hence are outwardly normal to the sphere at all points on its surface. The magnitude of the electric field E at a distance r from the point charge is equal to 1 by 4 pi epsilon naught Q by r square. Let this be equation 1. So we see that for all points on the sphere of radius r, the magnitude of the electric field strength is the same, and it is directed away from the charge plus Q in an outwardly normal direction at each point. Therefore, we see that at each surface point, the electric field strength E is parallel to the area vector dA, which represents the area of an infinitesimally small element on the surface. Since E is parallel to vector dA, the electric flux d phi passing through this local element is equal to E dot dA is equal to E dA cos 0, and as cos 0 is equal to 1, d phi is equal to E dA. Let this be equation 2. To find the total electric flux phi through the Gaussian surface, we now integrate d phi. Therefore, phi is equal to integral d phi, and this is equal to integral E dA. The total electric flux can also be referred to as the net electric flux. Since E is constant in magnitude for all points on the Gaussian surface, we have integral E dA is equal to E into integral dA. We know that integral dA is equal to A, which is the area of the Gaussian surface considered. Now, phi is equal to EA. We know that for a spherical surface, which is the Gaussian surface in the present discussion, A is equal to 4 pi r square. Therefore, we have phi is equal to E into 4 pi r square. Let this be equation 3. Substituting equation 1 in equation 3 and simplifying, we get the net flux phi is equal to Q by epsilon naught. Let this be equation 4. We see that the net flux phi is proportional to the charge Q enclosed by the Gaussian surface, or we can say that the net flux is proportional to the charge inside the Gaussian surface. Now consider two other closed surfaces, S2 and S3, around S1. We see that since S2 and S3 are closed surfaces, they can also be referred to as Gaussian surfaces. But it is important to note that the surfaces S2 and S3 are of arbitrary shape. We have seen that the net electric flux, phi, through S1 is equal to Q by epsilon naught. By definition, electric flux is the number of electric field lines passing normal to a given area. Here, we observe that the number of electric field lines that pass through S1 also pass through S2 and S3, normal to their surfaces. Hence, the net flux through S2 and S3 is equal to net flux through S1. That is, phi is equal to Q by epsilon naught. Here, we observe that the net electric flux phi through any closed surface is independent of the shape of the closed surface. Hence, we conclude that a Gaussian surface can be of any arbitrary shape. Thus, Gauss' law states that the electric flux through any closed surface is proportional to the enclosed electric charge. That is, phi is equal to Qin by epsilon naught, where Qin is the charge enclosed by the Gaussian surface. Let this be equation 5. Now consider a point charge Q placed outside a closed surface. Here, we see that the number of field lines entering the closed area is equal to the number of field lines leaving it. Therefore, the net electric flux through the closed surface is 0, and it is of importance to note that the Gaussian surface, which is the closed surface, was not enclosing the point charge. In other words, the net flux through a closed surface not enclosing any charge is 0. Let us consider a cube of side L placed in a uniform electric field of strength E, directed along the x-axis. As the cube is a closed area and the number of field lines entering the cube is equal to the number of field lines leaving it from any of its surfaces, the net flux through the cube is 0. Now let's prove the same. For any surface of the cube of area A, which is normal to the electric field of strength E, the electric flux phi passing through it is equal to EA. Now we see that the electric flux phi 1 through face 1 is equal to minus EA, since it has inward flux. And through face 2 it is phi 2, which is equal to plus EA, since the flux is outwardly normal to it. The flux through the faces 3, 4, 5 and 6, that is phi 3, phi 4, phi 5 and phi 6, respectively is equal to 0, since the area vector A is perpendicular to the direction of the electric field with respect to these faces. Therefore, the net electric flux through the cube is minus EA plus EA, which is again equal to 0. Now consider a system of discrete charges, say Q1, Q2, Q3, Q4, Q5, such that the charges Q1, Q2 and Q3 are inside the closed surface S, and the charges Q4 and Q5 are outside the Gaussian surface S. The resultant electric field strength E at any point will be equal to E1 plus E2 plus E3 plus E4 plus E5. The net flux of the resultant electric field strength E through the Gaussian surface is phi is equal to integral E dot dA, which is equal to integral E1 dot dA plus integral E2 dot dA plus integral E3 dot dA plus integral E4 dot dA plus integral E5 dot dA. Since charges Q4 and Q5 are outside the Gaussian surface, net flux due to these two charges is 0. Hence, the net flux on the surface is due to the three charges inside the Gaussian surface. That is, phi is equal to integral E1 dot dA plus integral E2 dot dA plus integral E3 dot dA. Therefore, phi is now equal to Q1 by epsilon naught plus Q2 by epsilon naught plus Q3 by epsilon naught. Or we can say that net flux through the Gaussian surface is equal to Q1 plus Q2 plus Q3 by epsilon naught. Let the total charge enclosed within the Gaussian surface be Qn, the subscript in referring to inside of the closed surface. Here, Qn is equal to Q1 plus Q2 plus Q3. Now the above equation for net flux can be written as phi is equal to integral E dot dA is equal to Qn by epsilon naught. Let this be equation 6. It is important to note that the electric field strength appearing in equation 6 is the net electric field strength E due to all charges present within the Gaussian surface and also outside the Gaussian surface. But the charge Qn appearing in the above equation is the charge within the Gaussian surface. In principle, Gauss law is used to calculate the electric field strength E due to a system of discrete charges or even a continuous charge distribution. From the above observations, we can look at some important points regarding Gauss law. Gauss law is applicable to any closed surface of any arbitrary shape. In the mathematical form of the Gauss law, we see that Qin is the sum of all the charges enclosed within the Gaussian surface, irrespective of their positions within the surface. The electric field strength appearing in the relation integral E dot dA is the net electric field strength E due to all charges present within the Gaussian surface and also outside the Gaussian surface. However, the charge Qin appearing in the above relation is the charge within the Gaussian surface. While choosing a Gaussian surface for a system of discrete charges, the Gaussian surface chosen should not pass through the system of the charges since the electric field is not well defined at the location of the charges, as it grows boundlessly as we move closer to the charge. However, in case of a continuous charge distribution, the Gaussian surface can be taken passing through the charge distribution. Symmetry is crucial to the application of Gauss law, since it makes the calculation of the electric field easier. Gauss law can be chosen to evaluate the electric field due to charge distributions that have spherical, cylindrical, or planar symmetry. Since Gauss law is based on the inverse square dependence on the distance contained in the Coulomb's law, any violation of the Gauss law indicates a departure from the Coulomb's law. In order to calculate the electric field due to a discrete charge distribution, we can apply the relation of the superposition principle. According to this principle, the net electric field strength E at any point in the field of the charge distribution is equal to the vectorial sum of the electric fields due to the individual charges at that point. This method of finding the net electric field at a point becomes impractical in the case of continuous charge distributions, such as a linear charge distribution, a planar charge distribution, or a volume charge distribution. In this module, we discuss about a linear charge distribution. Let us now consider an infinitely long straight wire carrying a uniformly distributed positive charge. Its linear charge density, lambda, is the charge per unit length of the wire. That is, lambda is equal to Q by L, where Q is the total charge on the conductor distributed over length L of the wire. The wire considered has an axis of symmetry. Consider a point O on the wire. Consider a radial vector from O to a point P whose magnitude is R. This radial vector is normal to the length of the wire. If we rotate the radial vector about the point O, we get a circle. Several points on the circumference of the circle obtained are equidistant from O. Hence, the electric field due to the charge on the element of the wire at O is equal in magnitude at all the points on the circumference. The direction of the field at any point on the circle is always radially outward. The fact that the electric field strength at any point is directed radially outward can be understood by considering two small elements of the wire at equal distances from O on either sides of it, as shown. Let the element at the point above O be A, and the element at the point below O be B. Then, the field at P due to the element at A, EA, acts along AP. Similarly, the electric field at P due to the element at B EB acts along BP. As the two elements A and B are equidistant from O, they are also equidistant from P. Thus, the magnitudes of the electric field strengths due to A and B at P are equal. To get the net electric field strength at P due to A and B, we resolve these electric fields into horizontal and vertical components. EA is resolved along AC and AO, which are along the horizontal and vertical directions. Similarly, the components of EB are along BD and BO, which are also along the horizontal and vertical directions. As the magnitude of EA and EB are equal and elements A and B are symmetric about O, the magnitudes of the horizontal components of the electric fields are also equal. Similarly, the magnitudes of the vertical components of the electric fields are also equal. We observe that the directions of the vertical components of EA and EB are opposite. Hence, they cancel each other. The horizontal components are parallel to the radial vector along OP. Thus, the net electric field at P due to the elements at A and B is equal to the sum of their horizontal components and acts radially outward. This is true for any such pair of elements considered on either side of the element at O. Thus, the field at any point under consideration, like P, is radially outwards. As the length of the wire is infinite, the electric field strength does not depend on the position of the point under consideration, P, along the length of the wire. Thus, the electric field due to the wire of infinite length is radial everywhere and in the plane normal to the length of the wire. It depends only on the magnitude of the radial vector r. Now let us calculate the electric field strength due to the charged wire at a point which is radially at a distance r from the wire. In order to calculate the electric field strength due to the wire, let us consider a Gaussian cylinder of radius r around the wire. Let the length of the Gaussian cylinder be L. According to Gauss' law, net flux phi through a Gaussian surface is equal to Qin by epsilon naught, where Qin is the charge enclosed within the Gaussian surface. Let this be equation 1. We know that phi is equal to integral E dot dA, where E is the electric field strength. At all points on the Gaussian cylinder, the electric field strength E is perpendicular to the curved surface of the cylinder. Since the electric field due to the charged wire points away from the positively charged wire as discussed earlier. If we calculate the net flux phi through the Gaussian surface, the net flux through the surface will be the sum of electric flux phi 1, phi 2 and phi 3 through the surfaces 1, 2 and 3 respectively, as shown. Surfaces marked 1 and 2 are the circular surfaces of the Gaussian cylinder, and the surface marked 3 is the curved surface of the cylinder. Let us now calculate the electric flux through surface 1, which is the flat surface of the cylinder. We know that the electric flux phi 1 is equal to E dot A, where E is the electric field and A is the area vector. This is equal to EA cos theta, where theta is the angle between the directions of electric field and the area vector. The electric field is perpendicular to this surface. Hence, in this case, theta is 90 degrees and cos 90 degrees is equal to 0. Hence, flux phi 1 through this surface is 0. Similarly, we see that the electric field is also perpendicular to surface 2, and hence flux phi 2 through this surface is also 0. Hence, the total electric flux phi is equal to the electric flux phi 3 through surface 3, which is the curved surface of the Gaussian cylinder. Let the surface 3 be assumed to be divided into infinitesimally small elements, each of area dA. There will be a net electric flux through this surface. Since the electric field strength E for any point on the surface is parallel to the area vector dA for the element under consideration. Since E will be parallel to the vector dA, we have electric flux d phi 3 passing through the element equal to E dot dA, which will be equal to EdA cos 0, and this will then be just equal to EdA. Let this be equation 2. To find the total electric flux phi through the Gaussian surface 3, we now integrate d phi 3. Therefore, phi is equal to integral d phi 3, and this is equal to integral EdA. Since all points on the Gaussian surface 3 are equidistant from the charged wire, the magnitude of electric field strength E for any point on the Gaussian surface is a constant. Therefore, we can write phi is equal to E into integral dA. We know that integral dA is equal to A, which is the area of the Gaussian surface considered. Therefore, phi is equal to EA. The area A is equal to 2 pi RL, which is the curved surface area of the cylinder of length L and radius R. Substituting the value of A in the expression for total flux phi, we get phi equal to E into 2 pi RL. Let this be equation 3. From equations 1 and 3, we see that E 2 pi RL will be equal to Q by epsilon naught. Let this be equation 4. Here, Q is equal to the product of the linear charge density, lambda, and the length of the Gaussian cylinder, L. Substituting the value of Q in equation 4 and simplifying, we get E equal to lambda by 2 pi R epsilon naught. Let this be equation 5. Vectorially, E is expressed as lambda by 2 pi epsilon naught into n cap, where n cap is the radial unit vector in the plane normal to the wire. Vector n cap will point away from the wire if lambda is positive, and it will point towards the wire if lambda is negative. From expression 5, we see that the electric field strength E, due to an infinite long straight wire, is independent of the L value. Therefore, the field strength is constant in both magnitude and in direction, thus representing a uniform electric field. Let us consider a thin spherical shell S of radius r. Let the thin spherical shell be uniformly charged with a positive charge Q. the surface charge density, sigma, is the charge per unit area of the surface, and hence sigma is equal to Q by A, where Q is the charge on the spherical shell and A is the area of the sphere. This can be rearranged as Q is equal to sigma A or Q is equal to sigma into 4 pi r square, since the surface area A of the spherical shell is 4 pi r square. Let this be equation 1. The electric field due to the uniformly charged thin spherical shell has a spherical symmetry, that is, every point on the surface of the shell is at the same radial distance from the center of the shell. The electric field strength at any point is equal in magnitude and is directed radially outward, that is, along the radius vector joining the point to the center of the spherical shell. Now let us apply Gauss law to derive an expression for the electric field strength at a point P1 outside the spherical shell and at a distance x from the shell. For this, let us imagine a sphere S1 of radius x around the charged thin spherical shell. Here, x is greater than r. This imaginary sphere S1 of radius x is a closed surface and it has area A1 equal to 4 pi x square. The imaginary sphere is the Gaussian surface. The electric flux d phi passing through a very small element of area dA1 of the Gaussian spherical surface S1 is equal to E dot dA1, which is equal to EdA cos theta, where theta is the angle between the directions of the electric field E and the area vector dA. Here, as E and dA1 are parallel to each other, theta is 0. Cos 0 is equal to 1. Therefore, d phi is equal to E dA1. The total electric flux phi is now equal to integral d phi, which is equal to integral E dA1. Since E is constant in magnitude for every point on the Gaussian surface S1, phi is equal to E into integral dA1. Now, integral dA1 is equal to A1, where A1 is the area of the imaginary Gaussian surface S1, which is equal to 4 pi x square. Therefore, total electric flux phi is equal to E into 4 pi x square. Let this be equation 2. We know that according to Gauss law, the total electric flux passing through the Gaussian surface S1 must be equal to Qin by epsilon naught, where Qin is the charge inside the surface. Let this be equation 3. Here, Qin will be equal to the charge Q on the spherical shell. From equations 2 and 3, we see that E into 4 pi x square is equal to Qin by epsilon naught. Substituting Q for Qin and simplifying this expression, we get the magnitude of the electric field E is equal to 1 by 4 pi epsilon naught Q by x square. Let this be equation 4. Equation 4 gives the electric field strength due to the uniformly charged thin spherical shell at the point P1, which is at a distance x from the spherical shell. By substituting equation 1 in equation 4, we can express the electric field strength E in terms of the surface charge density, sigma, as shown in equation 5. The electric field strength E can be expressed in vector form as E is equal to 1 by 4 pi epsilon naught q by x square into x cap, where x cap is the unit vector along the radius vector and directed away from the charged spherical shell. If the charge q is greater than 0, the electric field is directed outward from the center of the shell, which implies it is positive. On the other hand, if the charge is less than 0, the electric field is directed inwards, which implies that it is negative. Thus, for any point P1, which is considered outside the uniformly charged shell, the electric field due to the shell is as if the entire charge on the shell is concentrated at its center. Now, consider another point P2 inside the charged spherical shell, which is at a distance b from the center of the shell. To calculate the electric field strength at P2, draw a Gaussian surface S2 of radius b. Since the Gaussian surface S2 does not enclose any charge, Q in is equal to 0 for the given surface. Hence, net flux phi through this surface is 0. According to Gauss law, the integral E dot dA is equal to Q in by epsilon naught. Given that the Gaussian surface S2 has a surface area of 4 pi b square, and since Q in is 0 for S2, the electric field strength for any point within the Gaussian surface is 0. Thus, for all distances d from the center of the spherical shell, which are greater than its radius r, the magnitude of the electric field strength E due to the uniformly charged thin spherical shell is given by E, which is equal to 1 by 4 pi epsilon naught q by d square. For all distances d from the center of the spherical shell, which are less than its radius r, the magnitude of the electric field strength E due to the uniformly charged thin spherical shell is 0. An electric dipole comprises of a positive charge and a negative charge separated by a finite distance. Consider a dipole with a positive charge plus q placed at A and a negative charge minus q placed at B at a distance of 2a. This distance between the charges is referred as the length of the dipole. For an electric dipole, the midpoint O of the line joining the dipole is called the center of the dipole, and the straight line passing through the charges and also through the center is called the axis of the dipole. Assume that the dipole is placed such that the center O of the dipole coincides with the origin and the axis of the dipole coincides with the x-axis of the Cartesian coordinate system. The charge minus q is placed along the positive x-axis, and the charge plus q is placed along the negative x-axis. The product of the length of the dipole and the magnitude of the charge is called as the electric dipole moment P. Here, P is equal to 2aq. It is a vector quantity directed from minus q to plus q. Let us now obtain the electric field strength E at a point P on the axis of the electric dipole, which is at a distance x from the midpoint O of the dipole. The magnitude of electric field strength E due to a charge q at a distance r from it is given by E is equal to 1 by 4 pi epsilon naught into q by r square. Following the expression, the magnitude of the electric field strength E1 due to the charge plus q is equal to 1 by 4 pi epsilon naught q by x plus a square. Let this be equation 1. The direction of this electric field is in the direction opposite to that of the dipole moment. Similarly, the magnitude of the electric field strength E2 due to the charge minus Q is equal to 1 by 4 pi epsilon naught Q by x minus a square. Let this be equation 2. The direction of this electric field is in the direction of the dipole moment. The point P is nearer to the charge minus Q than the charge plus Q. As the distance of the point P from minus Q is lesser than that from plus Q, the magnitude of the electric field strength E2 is greater than E1. Hence, the magnitude of the resultant electric field strength E at the point P is equal to E2 minus E1. Let this be equation 3. The direction of the resultant field strength at the point is in the direction of E2. Substituting the values of E2 and E1 and simplifying, we get the expression for the electric field strength E is equal to 1 by 4 pi epsilon naught or AQX by x square minus a square whole square. Let this be equation 4. Simplifying equation 4, we get E is equal to 1 by 4 pi epsilon naught 2x into 2aq by x square minus a square whole square. In this equation, 2aq is the magnitude of the dipole moment P. Therefore, E is equal to 1 by 4 pi epsilon naught 2px by x square minus a square whole square. Let this be equation 5. When the point P is at a very large distance from the center O, then x is very large compared to A. Then, writing the expression 5 as in equation 6, and neglecting the term a square by x square for x which is very large as compared to A, in equation 6 and on further simplification, we get E is equal to 1 by 4 pi epsilon naught 2px by x power 4. Let this be equation 7. This can be further simplified as E is equal to 1 by 4 pi epsilon naught 2p by x cube. Let this be equation 8. In vector notation, equation 8 can be expressed as E is equal to 1 by 4 pi epsilon naught 2p by x cube into p cap, where p cap is the unit vector along the dipole axis in the direction of minus q2 plus q. Let this be equation 9. Let us now obtain an expression for the electric field strength at a point S on the equatorial plane of the electric dipole. Let point S be at a distance y from the center O of the dipole. The point S is at a distance r and is equal to root y square plus a square from each charge of the electric dipole. Let this be equation 10. At the point S, the positive charge creates an electric field of magnitude E1 is equal to 1 by 4 pi epsilon naught q by r square. Let this be equation 11. Electric field strength E1 is directed away from the positive charge and acts along the line joining the charge plus q and the point S as shown. Similarly, the negative charge creates an electric field of magnitude E2 is equal to 1 by 4 pi epsilon naught q by r square. Let this be equation 12. Electric field strength E2 is directed towards the negative charge and acts along the line joining the point S and the charge minus q as shown. We observe that the magnitude of E1 is equal to that of E2. The point S lies on the perpendicular bisector of the line joining the charges plus q and minus q. Hence, by geometry of the triangle SAB, the angle SAO is equal to the angle SBO. Let this angle be theta. Now the angle E1SE2 is the exterior angle of the triangle SAB, and hence this angle is equal to 2 theta. The resultant of E1 and E2 is obtained by using the parallelogram rule for vector addition. According to the rule, the resultant of E1 and E2 is obtained by the diagonal of the parallelogram formed by the vectors E1 and E2 as the sides. Since the magnitudes of E1 and E2 are equal, lengths of the vectors representing E1 and E2 are also equal. Hence, the diagonal of the parallelogram formed by the vectors E1 and E2 as sides bisects the angle 2 theta. Thus, the resultant of E1 and E2 makes an angle theta with the direction of both E1 and E2. By geometry of the figure, the resultant of E1 and E2 is parallel to the x-axis and is directed along AB. Let us consider the components of E1 and E2 along the x and y axes to find the magnitude of the resultant electric field at the point S. The components of the electric field E1 along the x and y axes are E1x and E1y respectively as shown. And the components of the electric field E2 along the x and y axes are E2x and E2y respectively as shown. Since the electric field strengths E1 and E2 are equal in magnitude, the components E1x and E2x will be equal. Similarly, E1y and E2y are also equal. We also observe that the components E1y and E2y are oppositely directed and hence they cancel each other. Therefore, at the point S, the resultant electric field strength E is equal to E1x plus E2x. Let this be equation 13. As the angle between E1 and x-axis is theta, the component E1x is equal to E1 cos theta. Substituting the magnitude of E1, we get E1x is equal to 1 by 4 pi epsilon naught into q cos theta by r square. Let this be equation 14. Similarly, the angle between E2 and x-axis is theta, and hence E2x is equal to E2 cos theta, which is equal to 1 by 4 pi epsilon naught into q cos theta by r square. Let this be equation 15. Substituting equations 14 and 15 in equation 13 and simplifying, we get the magnitude of the electric field at the point S. E is equal to 1 by 4 pi epsilon naught into 2q cos theta by y square plus a square. Let this be equation 16. From trigonometry of either of the triangles SAO or SBO, we get cos theta is equal to a by r. Substituting the value of r, we get cos theta equal to a by square root of y square plus a square. Let this be equation 17. Substituting equation 17 in equation 16 and simplifying, we get the equation for the magnitude of the resultant electric field strength E at point S. Since the dipole moment P is equal to 2aq, we get E is equal to 1 by 4 pi epsilon naught into P by y square plus a square whole power 3 by 2. Let this be equation 18. The direction of the electric field strength at the point S is opposite to that of the electric dipole moment and parallel to the axis of the dipole as discussed earlier. When the point S is at very large distance from the center O, then y is very large as compared to A. Then, writing the expression 18 as in equation 19 and neglecting the term a square by y square for y which is very large as compared to A in equation 19, and on further simplification we get E is equal to 1 by 4 pi epsilon naught P by y cube. Let this be equation 20. In vector notation, electric field strength E can be expressed as shown in equation 21. The minus sign is used since the electric field strength E is opposite to the direction of the unit vector P cap. For a given dipole, the magnitude of the dipole moment P is constant. From the expression of the dipole moment, we get charge Q is equal to P by 2A. Hence, as the length of dipole 2A tends to 0, the magnitude of the charge Q tends to infinity, so that the dipole moment P is equal to 2AQ becomes finite. Let us now look at the physical significance of a dipole. A molecule having positive and negative ions possessing charges of equal and opposite magnitudes behaves like an electric dipole. In certain molecules, known as non-polar molecules, the centers of all positive and negative charges coincide. Hence, in such molecules, there is no dipole moment set up. However, when a non-polar molecule is placed in an external uniform electric field, the electron orbits get distorted due to the force exerted by the external electric field. This results in the separation of the centers of positive and negative charges. The negative charges move in the opposite direction of the electric field, whereas the positive charges move in the direction of the electric field. This motion of the charges now sets up an induced dipole moment for the molecules, and the molecules are said to be polarized. When the external electric field is removed, the polarization disappears. Hence, the induced dipole moment also vanishes. Carbon dioxide, CO2, and methane, CH4, are examples of such non-polar molecules. There are other types of molecules called polar molecules, where the centers of the positive and the negative charges do not coincide. They possess some dipole moment even when they are not in the presence of an external electric field. Such molecules are called polar molecules. These are permanent dipoles. When such polar molecules are placed in an external uniform electric field, they orient themselves in the direction of the field. Water molecule H2O is one such polar molecule. Consider a permanent electric dipole having a positive charge plus Q at A and a negative charge minus Q at B separated by a distance 2A. A permanent dipole is one which has a dipole moment irrespective of the presence of an external electric field. The electric dipole moment P of the dipole is equal to 2AQ, directed from minus Q to plus Q along the axis of the dipole. Let the electric dipole be placed in a uniform external electric field of strength A, with its axis AB making an angle theta with the direction of the external electric field. Now, the charge plus Q of the dipole experiences a force F is equal to QE in the direction of the external electric field, and the charge minus Q of the dipole experiences a force F is equal to QE in the opposite direction of the external electric field. We see that on the dipole there are two equal and opposite forces along different lines of action, and hence we can say that the dipole experiences a couple which is the net torque on the dipole. This couple rotates the dipole until it is aligned with the direction of the external electric field. However, the net force on the dipole is zero, since it experiences equal and opposite forces. Since the net force on the dipole is zero, the couple on it is independent of the origin. The magnitude of the torque on the dipole is equal to the product of the magnitude of each force F and the length of the couple arm AD. The torque tau is equal to F into AD. Hence, tau is equal to QE into AD. In the triangle ADB, sin theta is equal to AD by AB. Since AB is equal to 2A, we have sin theta is equal to AD by 2A. Therefore, AD is equal to 2A sin theta. Substituting the value of AD in the expression for torque, tau, we get tau is equal to QE into 2A sin theta, or tau is equal to 2A QE sin theta. But the dipole moment P is equal to 2AQ. Therefore, we have torque tau is equal to PE sin theta. This is the expression for a torque experienced by a dipole when placed in a uniform external electric field. Since PE sin theta is equal to P cross E, we have torque tau is equal to P cross E. If the angle theta is equal to 90 degrees, sin theta becomes 1, and hence the torque on the dipole reaches its maximum. Tau max is equal to PE. Hence, we see clearly that the torque on the dipole is maximum when the dipole is held perpendicular to the direction of the external electric field. When the dipole is placed such that its axis AB is parallel to the external electric field, then the angle theta is equal to 0 and sin theta is 0, and hence the torque on the dipole is equal to 0. When the dipole is placed such that its axis AB is antiparallel to the external electric field, then the angle theta is equal to 180 degrees and sin theta is 0, and hence in this position also the torque on the dipole is equal to 0. From this discussion, we see that the expression tau is equal to PE sin theta will be valid only when the dipole is in a uniform external electric field. But when it is placed in a non-uniform external electric field, then the charges plus Q and minus Q of the dipole do not experience equal and opposite forces. Each experiences a force of unequal magnitude, say F1 on plus Q and F2 on minus Q, in different directions depending on the direction of the electric field strength at their respective locations. Hence, there is a net force on the dipole. In an external electric field of increasing magnitude, if the dipole is placed such that the dipole moment is in direction of the increasing field, then the net force on the dipole will be in the direction of the increasing field. Conversely, if the dipole is placed such that the dipole moment is in a direction opposite to that of the increasing field, then the net force on the dipole will be in the direction of the decreasing field. In general, the net force on the electric dipole depends on the angle made by the dipole moment with the external electric field. We know that when a dry plastic comb is run through dry hair, it gets charged by the method of friction. This dry comb can then attract pieces of paper. Here the pieces of paper are not themselves charged, but the electric field created by the charged comb induces a net dipole moment in the pieces of paper in the direction of the electric field. The electric field of the comb is non-uniform, and it exerts a net force on the pieces of paper having a net induced dipole moment. Thus, the pieces of paper move towards the comb because of the net force on them. Let us consider an infinite plane sheet of charge carrying a uniformly distributed positive charge. Its surface charge density, sigma, is the charge per unit area of the sheet. That is, sigma is equal to Q by A, where Q is the charge on the sheet distributed over an area A. We can represent it as Q in is equal to sigma into A. Let the sheet be aligned parallel to the YZ plane such that the normal to this plane sheet of charge is along the x-axis. The electric field due to the positive charge will be directed away from the positive charge. In order to calculate the electric field strength, at a point P near the sheet of charge, let us now consider a Gaussian cylinder, one of the plane faces of which passes through P, and as such, the plane face is parallel to the plane of the sheet of charge. The point P is at a distance x from the sheet of charge. The point P lies on the circular surface of the Gaussian cylinder. We see that the cylinder extends to the other side of the sheet of charge and the plane faces of the cylinder are equidistant from the plane sheet of charge. Let the plane circular faces of the cylinder be marked as 1 and 2, and the curved surface of the cylinder be 3. The total electric flux, phi, through the Gaussian cylinder is the sum of the electric flux, phi 1, phi 2, and phi 3 through the surfaces 1, 2, and 3 respectively of the Gaussian cylinder. Let this be equation 1. Let us first calculate the electric flux phi 1 through surface 1. According to Gauss law, we can write phi 1 equal to integral d phi 1. Here, d phi 1 is the electric flux through a small element of area dA on surface 1. d phi 1 is equal to E dot dA, where E is the electric field strength at the local element considered, and dA is the area vector with respect to the local element considered. Since E and dA are parallel to each other, E dot dA is equal to EdA cos 0, which is equal to EdA. Let this be equation 2. It is important to note that E is constant in magnitude for all points on S1. Now, phi 1 is equal to integral EdA. Since E is a constant, it is taken out of the integral. Then, phi 1 is equal to E into integral dA. Integral dA is equal to A, where A is the area of S1. Therefore, we get phi 1 is equal to EA. Since surface 2 is equivalent in all aspects to surface 1, the electric flux through surface 2, phi 2, is also equal to EA. Now consider surface 3, which is the curved surface of the Gaussian cylinder. At every point on the Gaussian cylinder, the electric field strength E and the outward normal to the surface, which represents the area vector, are perpendicular to each other. As the angle between the area vector and the direction of the electric field is 90 degrees, and as cos 90 degrees is 0, we have the flux phi 3 is equal to EdA cos 90, which is equal to 0. Hence, no flux passes through this surface. Thus, the flux phi 3 through this surface is 0. Substituting the values of phi 1, phi 2, phi 3 in the expression for total flux phi, we get phi equal to 2EA. Let this be equation 3. According to Gauss law, phi is equal to Q in by epsilon naught. Substituting the value of Q in, we get phi is equal to sigma A by epsilon naught. Let this be equation 4. From the equations 3 and 4, we get 2EA equal to sigma A by epsilon naught. Simplifying this expression, we get E equal to sigma by 2 epsilon naught. Let this be equation 5. The expression for the electric field due to the infinite plane sheet of charge shows that the electric field strength due to it is independent of x. Vectorially, E is equal to sigma by 2 epsilon naught into n cap, where n cap is the unit vector perpendicular to the plane and passing away from it. If sigma is negative, then n cap will point towards the sheet of charge, and if sigma is positive, then n cap will point away from the sheet of charge. Thus, for an infinite large planar sheet of charge, the expression for E as given by equation 5 is approximately true in the middle regions of the planar sheet, away from the ends.